So we will be looking at the buffer capacity and pH range. First, I have two beakers here. The first one has 1 molar of acetic acid with 1 molar of the acetate ion. Is this a good buffer? Yes, it's a good buffer because you have a weak acid and its conjugate base. On the other beaker, you have the same substances, but this time it has 2 molars of each. Would this be a good buffer? Yes, because you have a weak acid and its conjugate base. What would be the pH of these buffers? Well, the pKa of acetic acid is 1.8 E-5. So it's going to be around pH 5. What about this one? It'll be the same as the same acid. What's the difference between these two? Well, the one with 2 molar has more in it. Therefore, it has a higher capacity. That means if you add 1 molar of NaOH or OH minuses, you are going to run out of the acid. But if you add 1 molar of OH minus here, you will only use half of your acid and you will still have some more to use for the future. So that's what buffer capacity is. The buffer capacity is the amount of substance you have in your buffer that can interact with the acid. Okay. It is the amount of acid or base your buffer can neutralize before the pH begins to change. It depends on how much you have in the beaker. Do you have 1 molar or 2 molar? The more you have, the better. The pH range is the range of pH values over which a buffer system works. So if the pKa here is about 5, then it's good from pH 4 to pH 6, so plus or minus 1. The pH is going to depend on pKa, of course, and the amount of base and acid that you have in there. If you have equal amounts, the pH will be pKa. If you want it to be a little bit above or below the pKa, you can tweak the amount of base and acid. It is always best to make your pKa close to the desired pH because it's better when you have equal amounts of this, so it can interact with, it can resist the change in both directions when you add H plus and OH minus. In general, if the concentrations are different by 10 times, that means you have 10B and 1A, your buffering action is poor. So it's better if they're about the same. Okay? So what happens when you add a strong acid or a strong base to your buffer? Well, the buffer will attack whatever you add. So here we have 2 molar of the acetic acid and 2 molar of the acetate ion, its conjugate. So let's find the pH of this buffer. To do that, we're going to use Henderson Hasselbach. pH equals to pKa. Ka is 1.8 E-5 of acetic acid. We're going to take the negative log of that, and that will give us the pKa, which is 1.8 E-5 log 4.74, about 5, 4.74 pH. Okay, so it's 4.74 plus log of base and acid. Your base is 2 moles over 1 liter, so that is 2 molar. Acid is 2 moles over 1 liter, that is 2 molar as well. Okay, you can easily just use moles instead of liters because the liters will cancel anyway. So 2 moles to 2 moles, the same thing. Okay, so that cancels, it becomes 1, log of 1 is 0, so your pH is 4.74. Right now, you have a pH here of 4.74. And this is your buffer. You can buffer at this pH. What happens if you add something to this? What happens if you add some OH minus? Is your pH going to change? Well, it depends on how much OH minus you add. Let's say you added 1 mole of OH minus. Let's say you added 1 mole of NaOH. What's going to happen is this part of your buffer will react with that. OH minus. Okay, as a result, you're going to have, if you add 1 mole, how much of this will you have left over? You used 1 mole, right? So now you have oh, I didn't do this, did I? Oh, no, I'm sorry. So let me see what happens when we do it again. So pH is equal to pKa plus log of the base. So the acid. So first you had 2 moles. You used one of them because it reacted with 1 mole. What's left here? Well, you're left with 1 mole. So you put 1 mole there. Okay. So what happened is this acid turned into this substance. Now you have 3 moles of that. So that goes 3. So now your pH changes a little bit. Okay, so you might not see that, but when the OH minus attacks the H plus, you're going to make CH3COO minus, and you're going to make 1 mole of it. So now you used to have 2, now you have 1 more mole, now you have 3. Okay, so now plug that in. 3 divided by 1 is 3, log that. 0.477, you add that to the pKa. Your new pH is 4.74, 5.2. Okay, so your pH goes up a little bit, but not by much because some of the OHs were taken by all of the OHs were taken by this acid. Okay, so that's how buffers work. They just react with whatever you add. So to do this, you had to do stoichiometry. You have to see it's a 1-to-1 mole ratio. You have to recalculate how much you have in the end of the acid and the conjugate base, and you have to use Henderson Hasselbach. Okay, let's try an example. So you have a buffers made by that. So I'm going to go ahead and draw what I have in the beaker so I can really understand what's happening. So I have 0.300 moles of CH3 COOH and 0.300 moles of CH3 COO minus. I'm going to ignore the Na plus again and just put a minus there. Okay, that's that I just wrote down. To enough water to make 1 liter. So it'll be 0.3 molar. The pH of your buffer is 4.74. And it's 4.74 because that's the pKa, right? pH is equal to pKa if they're equal right now. Right now they're equal. Calculate the pH of the solution if you add this much NaOH. So you're going to add droplets of 0.020 moles of, I'm going to ignore the Na plus, OH minus pretty much is what you're adding. Okay. And you're assuming that it's still 1 liter in the end. Okay, so that's not changing. So, first thing you're going to do is think, what's going to attack the OH minus? That's right, the acid will. So you have to write the equation first. And this might be the hardest part of this, problem is knowing what equation to write. Well, of course, the acid will attack the base that you added in droplets, right? Okay, so what'll happen then is this will make water, of course, and you're going to make the conjugate base, CH3COOH. Okay, so now we're going to set up the ice box. In the beginning, how much do you have? I'm going to use molarity here, okay, because moles over liters. I have 0.300 moles for every 1 liter. That is, I'm going to use molarity. Okay, and I also have this much of this 0.300 molar again. So now I used to have, now I'm going to add this 0.02 moles inside 1 liter again. Again, that's molarity. What's going to happen? All of this is going to be attacked by this, right? So now all your base that you added has reacted with your buffer, and that's what you want, okay? So this will attack that, and you will make more of this. Oh, I'm sorry, this should be 00 minus, because this took that H, now it's a minus. Okay, so in the end you have less of this because you used it up. 0.300 minus 0.02 is 0.298. Now you have more of this, 0.302. Okay, so now you're going to do Henderson Hasselbach to find pH equals pKa plus log Ba. You're going to use Henderson Hasselbach to find the pH. pKa is 4.74. Plus log of base is 0.302 over 0.298. Okay. So you have 0.302 divided by 0.298 equals log 4.74 plus 0.00579. You can notice it's hardly changed. And then add that to 4.74. Your pH is 4.75. So what just happened? Your pH is still the same, even if you added some base. Okay, for comparison, what do you think will happen if you added that and you had no buffer? Let's try it. Okay, it says this. So if you had some water and you had a liter, remember we added 1 liter to that. Over here is 1 liter. We add the same thing, 0.02 mole of OH, 0.020 molar. It says that's moles of NaOH. Ignore that. I'm just concerned with OH minus. Well, if you have NaOH, you're going to have 100% dissociation, right? So all you have is 0.020 moles for every 1 liter, which is molarity. So that's your molarity of that, 0.020 molar. To get the pH of that, you're going to do negative log of 0.020. That will actually give you POH equals to 0.02 log 1.70. So POH and pH is, subtract that from 14, 12.30. Okay, so if you didn't have a buffer, your pH shoots up to 12. If you have a buffer, your pH stays at 4.75. That is wonderful. Okay, so that's what buffers do. Okay, let's try another problem. So it says determine the pH of the original buffer described in sample exercise 17.5. So you have, it's the same beaker, okay? You have a buffer right here, and I drew that right here. 0.300 moles inside 1 liter of the acid and the base, okay, in your buffer. Now, instead of adding NaOH, you're now adding some HCl. So you're adding drops of H+. Again, I'm ignoring the Cl-. Okay, and you have 0.02 moles of that. All right, I wonder who's going to attack that H+. You're right, the acetate ion will grab that. So the equation looks like this. The acetate ion, CH3COO-, will attack the H+ that you add in drops, right? And you're going to make CH3COOH. Okay? In the beginning, you have 0.300 of this, and that's molarity, moles over liters, over 1 liter. Over here, you also have 0.300 molarity. But now you're adding 0.02 of this. Okay? You're going to use all of it. All of it will be attacked by the conjugate base. So you will use that same amount of your conjugate base, and you will add the resulting conjugate acid because it's going to turn into this. So minus minus to the plus. Okay, so what do you have in the end? The acid that you added is gone. Now you have less of this, 0.280, and you have more of this, 0.302. 0.320. I think I might have an error here. Okay, it's right. So Henderson Hasselbach, pH is equal to pKa plus log of Ba. pKa is 4.74, same buffer, plus log of base is 0.280. Molar acid is 0.320. You're going to get 4.74 plus log of these two. I got whatever that is. Let me just calculate that. 0.28 divided by 0.32 equals log negative 0.0580. And then add that to 4.74. Your new pH is 4.68. Amazing, right? You added a strong acid and your pH hardly even moved, right? I wonder what happens if you add just that. Go ahead and do this problem. Pause the video. Okay, well, if you add 0.020 moles of HCl in 1 liter, you're going to have HCl is a strong acid, right? You're going to have 100% dissociation, H plus and Cl minus. So this is 0.020 moles, so for every 1 liter, it's just 0.020 molar, 0.020 molar, 0.020 molar. The pH will be negative log of the H plus, which is 0.02 molar, which is equal to 0.02 log 1.70. So if you add the same thing just to plain water, your pH drops to 1.7, but because you had a buffer, it stays where it was at 4.68.